Welcome to Revised Chemistry with Mr. B. In this video I'm going to take you through the entire chemical changes topic. That's if you're studying with AQA for combined science. If you're studying for separate science or you're with a different exam board, just check with your revision guide to see if there's any other extra little bits you might need to know. So let's get started by taking a look at the reactivity of metals. There are several reactions you can carry out to compare the reactivity of different metals, and one of them is reacting the metal with air by burning it, and when we burn it, it reacts with oxygen. So if I take this piece of shiny copper and heat it up with a Bunsen burner, it starts to glow red and eventually it will turn black because it's reacting with oxygen in the air to form a layer of copper oxide, but it's not a spectacular reaction. However, when we react a piece of magnesium with oxygen, then it gives off much more heat and light, and we can tell straight away that magnesium is much more reactive than copper. We can also see how different metals react with water. For example, this piece of copper doesn't react at all, it just sinks to the bottom, there's no reaction. Whereas a piece of sodium put into the water moves across the surface, it's making hydrogen gas, it's also making an alkali in the water, sodium hydroxide, and you can see it's burning with that orangey yellow flame. We can see that potassium is even more reactive than sodium. The reaction is much quicker and it's producing a lot more steam because it's even more exothermic. And we can also see that potassium burns with a lilac flame. Reacting metals with acid also gives us some clues about their reactivity. So I'm adding a spatula of iron to one test tube of acid and a spatula of magnesium to another, and we'll come back to that in a few minutes and see how they're reacting. So we can see the iron has got some very tiny bubbles of gas being produced, that will be hydrogen gas, but the magnesium is bubbling away much quicker, so we can tell that's a much more reactive metal compared to iron. When we've compared how different metals react with acid, oxygen and water, we can get an idea of the most reactive down to the least reactive. And when we put them in that order, we call it the reactivity series, with the most reactive at the top, such as potassium, sodium, calcium, magnesium, aluminium. This one in a different colour is a non-metal. Then we've got zinc, iron, tin, lead. And then just below that we've got hydrogen, which is another non-metal, and then some of the least reactive metals are copper, silver and gold. Now you are expected to remember this reactivity series for your exam, so how on earth are you going to do that? Well, luckily I've got a rhyme to help you. The way I remember the reactivity series is please stop calling me a cute zebra. Instead try learning how copper saves gold. And you can see here the metals that rhyme represents. I've got some silver coloured shiny iron nails that I'm going to place in some copper sulfate. So I'm reacting iron with copper sulfate. And I've also got some iron nails that I'm going to place in with some magnesium sulfate. And we'll come back to those in a few minutes and see what's happened. So the iron that was in with copper sulfate has reacted and it's turned an orangey colour because the iron has been coated in copper. If we compare that to the iron nails with the magnesium sulfate, nothing's happened, there's been no reaction. So why is it that iron will react with copper sulfate but it won't react with magnesium sulfate? When I put the iron with copper sulfate, there was definitely a reaction because the iron got coated in a layer of copper. And the reason for that is iron is more reactive than copper. We know that because it's higher up the reactivity series than copper. So what happened was iron took the place of copper. Iron became joined to the sulfate and that left copper on its own, and the copper coated the iron nail. So we say that iron displaces copper. In other words, it takes its place. When we put the iron in with some magnesium sulfate, there was no reaction. Absolutely nothing happened. And that's because iron is less reactive than magnesium. Iron is lower down the reactivity series than magnesium. So iron tried to take the place of magnesium, but it couldn't. We say that iron cannot displace magnesium, and that's because it's less reactive than magnesium. Our knowledge of the reactivity series can be used to predict whether a reaction will happen or not. So let's look at this example, iron plus aluminium oxide. Now if we check the reactivity series, iron is lower down than aluminium, so iron is less reactive than aluminium. So that means that it can't displace aluminium. It can't take the oxygen away from it and be joined to the oxygen. So if it can't displace aluminium, in this case we would get no reaction. However, if we had aluminium and iron oxide, aluminium is higher up the reactivity series than iron, so it's more reactive than iron. That means it can displace iron. So what we would make in this case is there would be a reaction, and it would make aluminium oxide, and we'd also get iron left on its own. So let's take a look at that reaction. It's a spectacular reaction called the thermit reaction. So what you're seeing first of all is a piece of magnesium burning to provide the activation energy. And now this displacement reaction is happening between aluminium and iron oxide. Aluminium is displacing the iron to form aluminium oxide, and we should get a piece of iron at the end of it. And here is that piece of iron that's formed at the end. Displacement reactions are often used to get metals from the rocks that they come from. So to get a piece of copper like this, let's first of all take a look at the rock that it comes from. Copper comes from a rock like this called malachite, and that's mainly copper carbonate. So the first stage of extracting copper from this rock is to heat up the copper carbonate. Imagine if we got that piece of malachite, the rock, and crushed it up, we'd more or less be left with some copper carbonate. So let's see what happens when I heat up this green copper carbonate, and I'll speed up the film so we don't have to wait ages. So we can see that the green copper carbonate has now turned into black copper oxide. What we've just seen is a thermal decomposition reaction where the green copper carbonate changed into black copper oxide and carbon dioxide was given off. It's called a thermal decomposition reaction because we're using a lot of heat, that's the thermal part, and the decomposition means that the copper carbonate is breaking down to form these two substances. But we've still not got the copper that we're trying to extract from the rock. The next stage is to take that copper oxide and heat it up with some carbon. So I'm going to put the copper oxide into a crucible, and I'm going to add equal amounts of carbon to it. And I'm going to make sure it's thoroughly mixed. Then I'm going to place the lid on the crucible and heat it up very strongly with the Bunsen burner. So here's the moment of truth. Have we managed to get any copper from that copper oxide? Let's have a look. And if we have a look here, what's this? There we go. That reddy colour that we can see there, that's the copper that we've extracted from the copper oxide. We're able to extract the copper from the copper oxide because we've just seen a displacement reaction. Carbon is higher up the reactivity series than copper, so that tells us that carbon is more reactive than copper, so it was able to displace copper. So the carbon took the oxygen to make carbon dioxide, and that left copper on its own. And we call this a reduction reaction because copper is losing oxygen. Reduction reactions are where a substance loses oxygen, and in this case we're using carbon to take the oxygen away from copper. The reactivity series can be used to summarise how we get metals from the rocks when we dig them out of the ground. So for example, gold is down at the bottom of the reactivity series, so no chemical extraction is needed. It's found as the pure metal itself, sometimes called the native metal. So gold wouldn't be joined to anything else. Whereas metals higher up the reactivity series are often joined to other elements such as oxygen. So if we were to get a rock that contained copper, it could be in the form of copper oxide. So we need to remove the oxygen from the copper. And we can do that by heating it with carbon if it's lower than carbon in the reactivity series. Now that wouldn't work for metals that are more reactive than carbon. For example, if we had aluminium oxide from a rock, we could try heating that up with carbon, but carbon is less reactive than aluminium. So it's not going to displace the aluminium. So for these metals that are more reactive than carbon, we use electrolysis to extract them from their ores. And the next topic that follows this is all about electrolysis. We're now going to look at the difference between oxidation and reduction. So we've already seen how if you start off with copper oxide and heat it up with carbon, the carbon reacts with oxygen to form carbon dioxide, and that leaves copper on its own. Now in this case, the copper is losing oxygen, and that is known as reduction. So we can say copper is reduced. So we say this is a reduction reaction because we're starting with copper oxide and it's losing oxygen to form copper. Now the carbon is the opposite. That's gaining oxygen to form carbon dioxide. And because it's gaining oxygen, we can say the carbon is oxidized. So while the copper oxide is being reduced, it's losing oxygen, the carbon is being oxidized, it's gaining oxygen. So the other word we can use for a reaction like this is redox, and that comes from the two words reduction and oxidation, because while this is being reduced, losing oxygen, this is gaining oxygen and being oxidized. So that stands for reduction and oxidation. This next 30 seconds is just for the higher tier students, so you might want to skip past this if you're doing foundation. So we can also think about oxidation and reduction in terms of electrons. And we need to remember this, oil rig. And that stands for oxidation is loss of electrons and reduction is gain of electrons. So if we look at this first example, some aluminium ions gaining 3 electrons to become aluminium atoms. They're having electrons added onto the ions, so they're gaining electrons, so that's an example of reduction. This second example, we can see we're starting off with some zinc atoms, we're making zinc ions and some electrons. In other words, we've taken those electrons from the zinc atoms, so they're losing electrons. So in that case, it's oxidation, because oxidation is loss of electrons. The next part of the topic focuses on different ways of making salts. And in chemistry, a salt is a substance made from an acid when that acid has had its hydrogen replaced by a metal. So what does that mean? Well, if we start off with sulfuric acid, for example, and react it with magnesium, the magnesium replaces the hydrogen of the sulfuric acid, and we get magnesium sulfate. So that's one example of a salt. The type of salt that you make depends on what acid you start with. For example, hydrochloric acid makes chlorides. So it could make things like sodium chloride or magnesium chloride. Sulfuric acid makes sulfates. So for example, it could make zinc sulfate. Nitric acid makes nitrates. There's 4 main ways of making a salt. The first way is metal and acid makes a salt and hydrogen. And the way I remember this is look at the initials MASH, MASH. So for example, if we had zinc as the metal and sulfuric acid makes sulfates, so it would make zinc, sulfate as the salt, and hydrogen. Second way of making a salt is an acid and a base makes a salt and water, and an insoluble base is often a metal oxide. So if we had hydrochloric acid and copper oxide, the salt would be copper chloride and water. Third way of making a salt is an acid and a carbonate. This time, instead of a salt and water, it makes salt, water and carbon dioxide. So remember, carbonate also makes carbon dioxide. So if we started with nitric acid as the acid and sodium carbonate, the salt would be sodium nitrate plus water plus carbon dioxide. And the final way of making a salt is an acid and an alkali makes a salt and water. So an alkali is usually something hydroxide, a metal hydroxide. So if we had sulfuric acid and potassium hydroxide, it would make potassium sulfate and water. So make sure you can remember these 4 different ways of making a salt. This is a good point in the topic to remind you a few things about chemical equations. One thing I'm always asked to give help to students is balancing equations. So rule number 1 about balancing equations is we can't change these small numbers here. What we can do is put large numbers called coefficients in front of the formula. So we could put a number there, or there, or there if we need to. And what we're trying to do is get the same number of sodium atoms on each side in this case, and the same number of oxygen atoms on each side. So let's first of all see what we've got on each side. So on the left we've got 1 Na, on the right we've got 2. On the left we've got 2 oxygens, and on the right we've only got 1. So it doesn't matter if we start with the sodium or the oxygen, so let's start with the oxygen. We've got 2 over here, but 1 here. We can't simply put a small 2 there. What we can do is put big numbers in front. So if I put a large 2 there, that means I've now got 2 lots of that. So I've got double what I had before. So I've now got 4 atoms of sodium, and I've got 2 atoms of oxygen. There's 1 Na2O, and here's another Na2O. Right, so the oxygens are now correct, they're balanced, but we've now got 4 sodium atoms on this side, only 1 over here. So now we need to go back to this side, and if we put a 4 there, multiply that by 4, we've now got 4 sodium atoms. So let's do a final check. We've got 4 Na, 2O, 2O. Notice how the Na and the O don't have to be equal, just with themselves. So equal numbers of Na on each side, equal numbers of O on each side. If you want more practice at balancing equations, including a few more tricky ones, I'll put a link up here now to another video all about balancing equations. This next 30 seconds is strictly higher tier only, so if you're studying foundation chemistry, then just skip along to the next 30 seconds. Okay, so what I'm going to show you is how to write an ionic equation. And we're starting with a symbol equation. And the first thing to do is spot where there's ions. So don't forget, ionic substances are made from metals and non-metals joined together. This is just a metal on its own, so it won't be made of ions. That will do metallic bonding. Here we've got a metal and non-metals, so that will be made of ions. It's made of copper ions and sulfate ions. Okay, here we've got metal and non-metals, so that will also be made of ions. This time we've got magnesium ions and sulfate ions. And then that's just a metal on its own, so that is just simply atoms. Right, so that's all the ions and atoms involved. What we need to do then is spot any ions that aren't changing from the start to the finish. And we can see at a glance that the sulfate ion stays exactly the same on both sides. So we can actually get rid of that. It's what we call a spectator ion, because it just sits on the sidelines watching without taking part, just like a spectator at a sporting event. So let's now write out the ions and atoms that we're left with. And we've got magnesium atoms plus copper ions changes into magnesium ions and copper atoms. So that is our final ionic equation. The required practical for this topic often asks you how to make a salt, and it could ask you how to make a salt with an acid and a carbonate, or it could also ask you how to make a salt using an acid and a base, and both methods are very similar. So it's this method of making a salt that I'm going to focus on to show you the required practical. So imagine the required practical wants you to make some copper sulfate crystals using an acid and a base. Well, first of all, we need to choose the right acid, and to make copper sulfate we're going to need sulfuric acid. And the first thing you need to mention in your answer is the quantities of the chemicals you're going to use. So a measuring cylinder goes up to 100 centimeters cubed, so anything like 25 or 50 would be a sensible amount. So in my practical, I would say first of all, to make copper sulfate crystals, I'm going to measure out 25 centimeters cubed of sulfuric acid using a measuring cylinder, so make sure you mention the equipment as you go along, and I'm going to pour that into a beaker. I'm then going to warm up that acid to increase the rate of reaction. In other words, it's going to make it react more quickly. To make copper sulfate, the base we're going to use is copper oxide. So first of all, we add a small amount of copper oxide and stir it, and we should see very soon that that turns into a blue solution as it reacts with the sulfuric acid to make copper sulfate. We then keep adding more copper oxide until we've added excess, and the reason we're doing that is to make sure all of the acid has reacted, and we'll know when we've made excess when it stops reacting and the excess copper oxide will settle at the bottom as some excess black powder. The next stage is to filter out that excess copper oxide, and we should get some blue copper sulfate solution, because what we're making from an acid and a base is a salt and water. So we've got our blue copper sulfate in water, we've got copper sulfate solution. We then need to evaporate the water from the copper sulfate solution, so we pour it into an evaporating dish that's on top of a beaker half filled with water. That's acting as a water bath so that we're heating it up in a more controlled manner than just having it straight on the gauze. So we keep heating it up until either half of the liquid disappears or until we start to see crystals around the edge of the solution. Now that only half of the solution remains, I would let this cool and put it to one side for the rest of the water to evaporate naturally. When we return to the crystals, they then need drying. The simplest way to do that is to pat them dry with a paper towel, or alternatively, you could place them in an oven to dry. This is the pH scale, and it's a measure of how acid or alkaline a substance is. So pH 7 in the middle is for a neutral substance. Anything less than 7 tells you it's an acid, and anything more than 7 tells you that substance is an alkali. And we can see that with acids, the further away you get from 7, so going down towards 1, it becomes a strong acid, whereas nearer 7, it's a weak acid. That does mean that for acids, as the pH number gets lower, the acid is getting stronger. Above 7 is for alkalis, and we can see that as you go towards pH 14, it becomes a strong alkali, whereas near 7, pH 8 or 9, that's a weak alkali. These colours represent the different colours that universal indicator goes with different substances, and I'll show you some of those now. I'm going to pour a small amount of lemon juice into the drop-in tile and add a few drops of universal indicator, and we can see by that bright red colour it's a strong acid, probably pH 2. I'm going to do the same thing with some antibacterial hand gel. And I'll give it a little stir just to make sure it mixes in properly. And we can see this time it's an orange colour, that's suggesting pH 4 or 5, so it's a weaker acid than the lemon juice. We're now going to look at why you get strong and weak acids and alkalis. So we've seen from the practical the pH scale, notice the small p and capital H, and strong acids are pH 1 or 2
on the pH scale. So that would go a dark red with universal indicator. 5 and 6 would be a weak acid, pH of 8 or 9 would be a weak alkali, and pH of 13 or 14 would be a strong alkali. So strong acids fully dissociate, that means fully breaks down to release lots of H plus ions, hydrogen ions, and it's these hydrogen ions that make it an acid. The more hydrogen ions there are, the more acidic it is. So if we take the example of hydrochloric acid, HCl, that fully dissociates to produce lots of hydrogen ions and also chloride ions. In the case of weak acids, they only partially dissociate to release less hydrogen ions. So if we look at ethanoic acid, also known as vinegar, that partially breaks down to release hydrogen ions and the ethanoate ion, but we can see it's a reversible reaction. So some of those hydrogen ions and ethanoate ions recombine to form ethanoic acid. So the end result is there will be less hydrogen ions in there. It's only partially dissociating. So in the case of strong alkalis, they fully dissociate to release lots of hydroxide ions, which are OH- ions, and they're what make it an alkali. So sodium hydroxide is a strong alkali that fully breaks down to release sodium ions and lots of hydroxide ions. Weak alkalis only partially dissociate, so they will release less hydroxide ions. So in this case we've got ammonia dissolved in water, and that produces something called an ammonium ion and hydroxide ions. But once again, it's a reversible reaction, so some of those products will change back into the reactants, meaning we've got less hydroxide ions, so it's a weaker alkali. A neutralization reaction is when an acid reacts with an alkali, and the hydrogen ions from the acid react with the hydroxide ions from the alkali to form water. So that's why when we react an acid and an alkali together, a salt and water are formed. And this is called the Ionic equation for neutralization. And this is something that you definitely have to learn. If you're studying for the higher tier paper, you need to know what pH means in terms of hydrogen ion concentration. So remember, all acids dissociate or ionize to produce hydrogen ions. And the pH scale is a measure of the concentration of hydrogen ions in the solution. So if we look at this table first of all, we can see the pH going down the side from 0, a very strong acid, up to 6, a weak acid. And down the middle we've got the concentration of hydrogen ions. And they're in standard form, but you can see the power of the standard form, -1, -2, -3, that corresponds to the pH number. So if something has a pH of 4, it's got a hydrogen ion concentration of 1 × 10⁻⁴. So if we put that as ordinary numbers, we can see that a strong acid, maybe with pH 1, has got a concentration of hydrogen ions of 0.1, whereas a weak acid, which has got a pH of 6, the concentration of hydrogen ions is 0.000001, so there's far less hydrogen ions in solution with the weaker acid. If we transfer that information onto our pH scale, we can see that the strong acid with a pH 1 has a hydrogen ion concentration of 10⁻⁻1, pH 2 is 10⁻², and so on till we get to a weak acid with a concentration of 10⁻⁶ hydrogen ions. And if we put a couple of ordinary numbers in there, we can see how the stronger acid with the pH of 1 has got a 0.1 mole per dm³ hydrogen ion concentration, whereas the acid with a pH of 6 has got a much lower concentration of hydrogen ions.
I'm now going to use this equipment to track the pH changes during neutralization. So I've got some alkali in the flask, and I'm going to gradually add in some acid from the burette to neutralize the alkali. And rather than using universal indicator to track the pH, I'm actually going to use a pH probe, which will give me a digital readout to 2 decimal places. So for example, rather than the pH saying pH 13 with indicator solution, this would say something like pH 13.2 0.24, for example. So we say it's got a higher resolution. So I start by taking the starting pH before I've added any acid to the alkali. And this alkali is a strong alkali because it's pH 13.22. I then run in carefully 1 centimetre cubed of the acid, give it a stir, take the new pH and continue with that until I've neutralised the alkali. And now I'm going to show you a set of results that you would get if you did an experiment like this.
These are a typical set of results that you would get when you're tracking the pH during a neutralization reaction. You can see at the start the pH doesn't change very much at all, so you can see why we needed the pH probe with the high resolution, because it was only changing from 13.55 to 13.45. So if we just got universal indicator paper, that wouldn't show up that type of small change. So to start with, there's not very much change at all in the pH, but then as you get nearer the point of neutralization, when you get towards 13, 14, 15 centimeters cubed of acid added, then there's a much more dramatic change in the pH. When you plot these results, you can see a very distinctive shape to the pH curve. To start with, as acid is added, the pH only starts to creep down very slowly, and then either side of the point of neutralization, the pH dramatically changes, and then once neutralization has occurred, the pH levels off again. So what could you be asked on an exam? Well, first of all, you could be asked how to obtain a pH curve like this, and you would describe the experiment I've just showed you in the video. Or you could also get a question like this: what volume of acid was needed to neutralize the alkali? So first of all, you need to remember that pH 7 is neutral. So with a pencil and ruler, you would draw on the graph in your exam a line from pH 7 until it hits the pH curve. And then you would draw another line again with the ruler down from that point, and in this case it looks like 14.5 centimeters cubed. You could also be asked a similar question like this one: what was the pH after 9 centimeters cubed of acid had been added? This time we need to draw up from the x-axis. So we find 9 on the x-axis, draw a line with the ruler up until it hits the pH curve, and then draw across to read off the pH. Now I've just estimated for this one about 13.2. It would be much easier in your exam because you'd have proper graph paper and you'd be expected to read off to the nearest tiny square. This one is a much trickier question. So the question tells you 25 centimeters cubed of acid was placed in a flask and an alkali was gradually added to it. Sketch the shape of the pH curve you would get, and then mark on it the point of neutralization. So because we're starting with an acid, it's going to be a low pH. So I've decided it's a strong acid, and I'm starting off between pH 1 and 2, and as the alkali is added, it only creeps up to start with. Then around neutralization, the pH shoots up, there's a dramatic change, and then it levels off once again. So they wouldn't be expecting you to put any numbers on this, it's just the general shape that you would need to be able to draw. And in terms of where neutralization happens, once again you would draw across from pH 7 with your ruler, and then you can mark on where neutralization is occurring. If you found the video useful, please remember to like and subscribe. Thank you for watching.